All right, so we're going over our labs. We had lab 19. I'm going backwards because I can't count forward. 18 and 17. Here are our three labs that we did. Okay, in 17, we took an empty Erlenmeyer flask and we were able to come up with the molecular mass, fancy M, for helium and argon. Okay, and we used the following formula. Molecular mass is equal to dirt over P. All right, and the key for this lab was that we had to have an evacuated flask. So we couldn't work inside a vacuum, we'd choke. So what we did was we took the density of the air, 1.17 grams per liter. We figured out the volume by filling it up with water and then pouring it into a graduated cylinder. So knowing the density of air and the volume, we solved for the mass of the air. So we measured this container on a scale. With the calculations of the density of air and knowing the volume, we solved for the mass of the air in there. We subtracted that and then we had the evacuated flask. And after that, everything else is pretty straightforward. We put these on the tanks. One went upside down and one went the other side based on density. And knowing, hey, okay, the mass of the flask and air that went in the container, knowing the volume, knowing the atmospheric pressure, because this is an open system, the pressures in the atmosphere, okay, and of course knowing the temperature, we were able to solve for the molecular mass. Okay, and that was pretty straightforward, but an important way to do that lab. In lab 18, we collected a gas by water displacement. And if you remember, we used a graduated cylinder upside down. And if you remember, there was going to be some water here. Okay. And we collected butane. But because we collected it by water displacement, and water is always evaporating, we also collected water vapor. Okay. And this was a little more advanced lab because we had a couple of things involved here. Number one, we had pressure total in the flask was equal to the partial pressure of the butane, C4H10, plus the partial pressure of the water. Okay, now, in order for us to even get to the total pressure, we had to do a manometer problem, right? We had atmospheric pressure. So unlike this system, which was open to collect the air, this system, the pressure total did not equal the atmospheric air, okay? And knowing the atmospheric air pushing down on the water to support that liquid, knowing the atmospheric pressure, and knowing the height of water, which we converted to mercury, we're able to calculate with a manometer problem what the total pressure was. To get this point, we used a manometer problem. Now, I should have told you, but I didn't want to, we could have circumvented the manometer problem. If I used a deeper water bath, all I could have done is just push this down so the levels were equal and we didn't have to have the manometer problem. I know, but I want you to go through it, okay? Or if I did what? Add more of the what? Butane so it equaled the water. Hey, if the levels are equal, you wouldn't have the manometer problem. You have to convert the height of the water to mercury. Oh my God, height times density. Sorry, okay? I forgot, okay? But if they ever ask you, how do you fix this to make life easier? Make the levels equal. Make your manometer levels. So just either add more gas to its equal or get a deeper container and push that up. And when the levels are equal, you have no manometer. Pressure outside equals pressure inside. Oh, well, any case, all right? But eventually, party people, we were trying to get the molecular mass of butane. So again, we still use molecular mass equals dirt over P. But the dirt, of course, is grams over volume, okay? Understand that the pressure that we're using to solve for the molecular mass of butane had to be just the partial pressure of the butane, okay? We'll get back to the errors in a second. And in lab 18 was a Boyle's law, okay? This we had...
You mean 19?
Yep, we had a syringe. God, I wish I see you guys every day. And in that syringe, okay, we had a pressure
Yeah, ours is broken.
gauge.
Yes, it was.
It's okay.
Like, this is one
Broken.
Okay, and this, of course, went to a computer. The computer screen did what? It eventually plotted a pressure, volume, and we got an inverse relationship curve there. Okay, now, the real star of that lab is the relationship was that volume is equal to 1 over P times a constant. And then when you solve for pressure, you get pressure times volume equals K. And what I was asking you to do, and I found out yesterday that people couldn't read off their graphs, okay? But I wanted you guys to take the pressure values that you plotted, or the computer plotted, okay, and times them together to find the values of K, okay? And the whole point of that lab was to see where this K changes. It should stay constant, right? As pressure goes up, volume goes down just as much to keep that number constant. But that assumes a couple of things, okay? And we'll talk about that. So those are the 3 labs. All 3 of them have something in common, okay? They all are built by PV equals nRT, okay? They all use that relationship that we, okay, derive together. And this is called the ideal gas law equation. I call it the static, but now it's called the ideal gas law equation. Ideal gas law equation. That's where you'll hear it. Why is the ideal gas law equation? Because what we solve would be perfectly correct if the gases acted perfectly ideal. They don't. They don't. So every one of our labs has error built in because every one of our labs are using equations that are derived from relationships that have an assumption that gases are ideal. Well, they are real. They really have attractive forces. They really have some volume. And that's going to affect your outcomes differently in each of these labs. And this is where your AP or college level understanding has to jump from concept to application. And I love it. You have to understand it. So I'm asking you to write a conclusion. Just a small paragraph, nothing crazy, that hits on what the errors were in terms of the fact that we are dealing with real gases. So in every gas law scenario that is presented to you on the AP or in life, okay, when everything's derived from this equation based on ideal conditions, every one of your gas laws has error. But the error is a little bit different here based upon how we gather data and how it's set up. Let's start with number 17. Okay, so we're solving for molecular mass. Okay, now, what do we know? We know the pressure outside, so the pressure of the atmosphere, is going to equal the pressure in the flask. Why? It's an open system. Okay? So that's important. So here's the deal. We measured the pressure in the atmosphere. We read the barometer reading. So we have that. That's the pressure inside the flask. So the pressure measured is the pressure measured. So this right here is telling me exactly what the measured pressure is. That's not a problem. Okay? The problem is we're going to get a molecular mass which is going to be grams per mole. Now mole comes out of here. Okay? Now, so where is the problem here? Well, the problem is that in order to have this pressure of the flask, in order to have that pressure, aren't we going to need more or less molecules to make that same pressure if they're really attracting each other? This pressure is the same. But in order to have this pressure in here, if they really are attracting each other and have longer mean free paths, then don't we need more of them? Okay? So in order to get this pressure, we needed more grams. We measured the grams, but that grams is going to be an elevated value. if that was an ideal gas, you would need less of the what? Gas to produce that same pressure. And I think in here, in my mind, I think of gases coalescing like those beads to fill. They're attracting each other. So to produce the same pressure, I need a little bit more of them. So that means my gas, my grams that I measured, and hey, the grams is what you measure. You put the flask on without the gas, and the flask on with the gas. Assuming you fill them up and didn't leak any, the difference is the grams of the gas. You know, once you have the evacuated flask using the density stuff that we talked about. So because this gas is real, we need more grams to achieve that pressure, which is going to lead you to have a molecular mass calculated to be an overvalued, be a larger value than it should. That is the error in this lab. Now, of course, there's some other things you could write about it, but in terms of ideal gas law, that's the error. That's going to be an over-evaluation because we're going to require more grams to equal that same pressure because they are attracting, okay? Real gases. Okay, now, how much is that going to be? How much is that going to be? Who knows, okay? There could be other errors, like you didn't fill the flask up, you dumped some out. But in terms of just real gas behavior, we know that what we calculate for is going to be definitely a bit above than it should. Could there be other bigger errors? Yes. All I want you to really write about is the real gas behavior. Just leave the rest of it. I don't care if your values didn't come out as great as you wanted to, okay? But that's what I want to talk about. So that's this lab here. Okay. This lab is very similar, but it's the most complicated to explain the error built in. But we're going to go after it. Now, unlike this lab, the pressure in this container is not the same as the outside. It is definitely going to be less, but the problem is the total pressure in here is due to two gases, the butane and the water vapor. Now, think with me for a second. It's a little more complicated. We know that these gases are both going to be real, which means they both attract each other or themselves. Now, butane is completely nonpolar. Water is polar. So because of those major differences, water is not going to attract the butane significantly, but water will attract itself. Now, butane will attract itself. Things that are nonpolar do stick to other things that are nonpolar by LDFs. We'll get into that. So butane will attract itself, and we know butane does because I put butane in a little baggie. It boiled in your hand. It's okay. It boils at 0.5 degrees Celsius, not at negative 196 like nitrogen. So it does have attractive forces for itself that becomes significant enough for it to boil at 0.5 degrees Celsius. Okay, that being said, you can snap about that later. But the point is, or Instagram that. How do you say Insta? You say Insta something? How do you make it?
Post that.
Just post it? Okay, I'll be cool at some point. All right. I was doing so well until I asked them. When you start asking those questions, cool meter just drops. Yeah. Okay. Okay. Any case, I want to be edgy. All right. Any case. Now, so where's the issue? If butane attracted itself as much as water attracted itself, we'd have no error, even though they're what? Think about it. Still, let's pretend that 90% of the gas was butane and 10% was water vapor. Okay, that's how we're doing this, right? If they have the same attractive forces themselves, there's no error here. There wouldn't be any error, but water is polar. It's got a negative end and a positive end. It has H bonding. So water is going to attract itself more than butane attracts itself. Ooh. Think about that. If you've got a flask or a container and water attracts itself more, isn't it going to have a what? A more lowered pressure than the butane? Doesn't that mean if this has more attractive forces, the total pressure is the total pressure? That's the manometer problem. That's not being affected. Hey, that is what it is. But inside that container there, because water attracts itself more strongly than butane attracts itself, then water is not going to contribute equally to the pressure that butane does. In fact, it's going to do what? contribute less to the total pressure. That makes sense? I'll say that again. Because water attracts itself more than butane attracts itself, water is more of a real gas. So its individual partial pressure is more affected by its intermolecular attractions. So let's say its pressure is 20, it's supposed to be on a table, it says 20 torr at a certain temperature. Well, guess what? It's going to be lowered. And if it's 20 torr and the total system's 100 torr, this should be 80. 80-20, making things easy. But if this is attracting itself more than butane, that means it's less responsible for its share of the pressure than butane. So it's not 80-20, maybe it's what? 85-15. If this attracts itself more, that means that butane has a larger contribution to its partial pressure than to the water. Okay, you see that leap there? Which means that this pressure that we measured was undervalued. This thing was too low. And when you lower the pressure, which is in the denominator, what does it do to your molecular mass? Right, your molecular mass is overvalued. I'll do that again. In this container, both these guys are real gases. Water is more real because attractive forces are greater. What do we learn? The individual pressure is equal to total. Well, gosh darn it, because water attracts itself a lot more than butane, it's going to have its pressure lowered more. The pressure total is still there. That means that butane contributes to a larger percentage of the pressure than we accounted for. Because water contributes less because it attracts more. That pressure should be higher. But we didn't count for that, so our pressure is lower than it should be. Okay, which raises that up. That's a little trickier. But both of them are going to lead to an overvaluation of your molecular mass for different reasons. Well, for the same reason, but a different process. Same reason is attractive forces. Okay, last one. Okay, now this last one, when you talk about individual variables, hey, what does K represent? K represents an evaluation of temperature staying constant, yeah, right, and of course moles staying constant. So this pressure going up equals volume going down. Pressure quadruples, the volume goes down to a fourth. Same thing as saying the pressure increases 4 times, the volume goes down 4 times. Okay? So that, my friends, is an example of inverse. And that only works if this number stays constant. So what I'm asking you to do in your graph, where you have pressure and volume, I want you to multiply them. Yes, I asked them some questions to find the atmospheres per book and all that good stuff. But the real gem of the lab is to find the K. Now, if you can't see off your graph, I did post yesterday, use those values. And do pressure times volume. What am I after? I want to see is where K changes the greatest. And where do I think it changes the greatest? I think it will change the greatest. I don't know if it did. Again, if you can't read off your graph, use what I posted yesterday. Where's my syringe? Why can't I find anything? Oh.
Can we multiply every coordinate point?
Yes, I want every point, pressure times volume. It should be the same number if it's inversely related. But what do we know? Under high pressure, small volumes, what am I doing to my gases? Well, I'm pushing them closer together.
Increasing pressure.
And I'm increasing pressure. What am I doing to the gases if I push them together? What am I doing to their real gas behavior? Increasing it or decreasing it when I increase the pressure? When I push them closer together, what am I doing to the real gas behavior? Increasing it or decreasing it? Increasing it. You're forcing them closer. They're going to attract more. Hey, didn't we just do that graph? Wasn't there a dip? So I expect the volume to get smaller, the pressure should increase. But as I do this, the pressure doesn't go up as much as we expect because they start attracting more. So I think the value of K here is going to deviate a lot. And another problem, temperature stays constant. Hey, didn't I do that syringe demo? Hit down, it's going to get warmer. we didn't keep the same temperature. So as I go down, down, and down, this gets warmer as well. So that's going to deviate and change K. And these ain't perfect. Neither is my language, but these syringes are not closed systems. I would expect, as I get to the 5th book, that air is leaking out, which means the N is changing.
Yeah.
So I would expect that extreme to cause some issues. And, oh, wait a minute. As this gets lower and lower, doesn't the volume of the gas become a more significant part of the volume it's flying in? All of those reasons tend to give me that round this top part of the graph, my K should change really, really more than in the middle. The opposite end, where I pull back, or you guys pull back. Now, number 1, the temperature should drop. That's not going to stay constant. Okay? And what else? I don't think, well, this has to stay closed. Maybe gases are leaking in, okay? But I don't think that pulling out creates the problem of pushing in. Well, we'll see, okay? So pulling the syringe out, making the space bigger and the pressure dropping, moles could leak in. It's not a perfectly closed system. Temperature is going to decrease, so that should change K, okay? We're getting more ideal, so we're eliminating some of that real behavior pushing together. So I would think still the K is going to increase at this end or change, but not as much as at this top end. I don't know. I'm going to go, I can't wait my lunch period to go calculate that and see what happens. So, I'm not joking. I want to know, okay? You think I'm joking,
Can I help
okay?
you? I wanna know
All right.
too.
But I'm going to be edgy because I put a skull and crossbones on my calculator on the back side, okay? So I'm cool, all right? And so your written conclusion just surface around the values of K, okay? And try to talk through that. And again, don't give me more than just a simple paragraph. Are there other errors in the lab? Sure. But just focus your discussion on that, okay? All right. And that's all I want. Okay? So anytime you've got errors in gas laws, most of the time you're thinking about attractive forces. All right? So that's 17, 18, and 19 errors. Put the conclusion onto those labs, staple them, give them to me by Friday, and you're good to go.